Thanks. Yeah, the talk will be in two completely separate parts. So the goal of the first part is to explain some puzzling features of SYK kernels that actually I discussed at a workshop. It wasn't quite this workshop, but it was sort of associated to it last year. And these are properties of the SYK kernels that make it possible to analyze the Regge or chaos limit in the SYK model. This is the part of the 4-point function that's most directly related to the black hole horizon. And basically the puzzle was that there's multiple ways to access the Regge limit. One way is to do it directly in Lorentzian signature, and another way is by analytic continuation from the Euclidean correlator. And the puzzle was sort of why these two computations agreed. And this was explained by a general formula for conformal field theory that was derived by Karen Huo earlier this year. So I'm going to discuss an alternate derivation of that formula, which was appeared in a paper with Simmons, Duffin, and Witten. And I'll explain this alternate derivation in a way that makes the connection to SYK clearer.
Why was there a puzzle? Are you going to explain that? Isn't the Lorentzian always related by analytic continuation?
So, yeah, the thing is that there are, in SYK, there were two different types of kernels that you could discuss. One of them was the Euclidean kernel, and that allows you to compute the Euclidean correlation function. You can then take that and analytically continue it to the Regge region. There's another kernel, the retarded kernel, which directly gives you the chaos exponent in the Regge region. And these are different kernels. They have a different spectrum, but somehow the poles of the retarded kernel end up being relevant for the analytically continued correlation function. Actually, another thing which I should say before starting is that the situation here is a little bit dependent on dimension. And in SYK, we're in one dimension. I could explain that case, but what I'm going to explain is the more generic case, which is dimensions bigger than 1, and I can comment on the one-dimensional case at the end. So this will have to do with thinking about 4-point functions in a conformal field theory, and it will be helpful to make a type of analogy. Well, a couple of things. Vladimir's talk will be helpful because he set up some of this, but also it'll be helpful to make an analogy to a type of Fourier transform and our conformal field theory formulas.
Could you write a little bigger?
I will when I write something important. Okay. So we'll be considering the 4-point function. And for convenience, we'll imagine this is a 4-point function of operators that have the same conformal dimension. And to make it conformally invariant instead of covariant, we can divide it by products of 2-point functions.
Still needs to be bigger. It's still not important.
Well, I really don't want to write bigger than that. And I feel that if you're that far back, maybe you could move forward. I don't know. This is pretty big. Okay. So there are different ways of thinking about this object. And one way of thinking about this is as a vector in a Hilbert space. So we can think about this function as an element in a vector space of functions. And then we can expand it in a basis for that Hilbert space. And that formula is one that looks like what Vladimir wrote earlier, except in higher dimensions we have two quantum numbers, spin and the conformal dimension. And the expansion looks like this. So these are some coefficients in the expansion, and these are the basis elements for our basis for the space of functions. So just before I explain that, we could imagine a somewhat similar situation where, let's say, we're trying to expand a function of just two coordinates, x1 and x2. And let's assume that this is a translationally invariant function, and we also have a reflection symmetry. Then we could expand it in a complete basis of functions for that space, some coefficients. We could expand it in a set of these cosines. Okay, So these are just a complete basis for this space of functions. And notice that these cosines are eigenvectors of the Casimir operator for symmetry, which is translation symmetry. If we just act with that on one of the 2 points, so on x1, then the functions we're expanding in are eigenvectors with this eigenvalue p squared. So we're doing something extremely similar here. We have a more complicated symmetry group, but these functions, these partial waves, are analogous to the cosine. Sort of similar to the cosine, they're a sum of 2 terms, the block and the shadow block. And they are eigenvectors of the conformal Casimir operators acting on points 1 and 2. And they have eigenvalues that are related to the dimension and the spin, delta and j. So that's what these functions are. And here we're just expanding in the basis of those functions. So one thing to note about this is that the dimensions that we're integrating over here are an unphysical set of dimensions from the perspective of conformal field theory. These are reasonable dimensions from the perspective of a complete set of functions, but they're like complex dimensions, and they're not what we would expect in the operator product expansion. So to see how you get the OPE, we can go back over here for a second. And let's imagine that we knew that this function here was a sum of exponential decays in the difference of these coordinates. This form doesn't make that manifest. One way that we could make it manifest is we could split up the 2 terms in the cosine. We could then replace that by a single term integrated over the full range of momentum. And then we could shift the contour and pick up some poles in f tilde of p. Those poles are at values of the momentum that would determine the spectrum of exponential decays in this function. So that's somewhat similar to the OPE for this case, and that's how we would derive it. We split up this cosine in 2 terms, extend the region of integration to turn it into 1 term, plus an exponential, and then deform the contour and pick up these poles. So you do the same thing here. You separate this thing into the 2 terms. You write that as 1 term integrated over an enlarged region of integration in delta. Then you shift the contour over delta. You pick up poles in this coefficient function here, and that determines the set of operators that appear in the OPE. So it's important that this guy obviously contains all of the information about the 4-point function. Its poles are the locations of the operator dimensions. The residues are related to the OPE coefficients. Okay, so this was all thinking about the 4-point function as a vector in this Hilbert space of functions. There's a slightly different perspective that we could take, which we can again motivate over here, where we think about this not as a vector x1, x2, f, but we can think about it as an operator x1, f, x2. The same expression here we can think about in this way as a matrix. And then the operator f is, we can imagine basically writing this operator. This formula corresponds to a formula for this operator, which is an integral 0 to infinity dp f tilde of p times a projector. Okay, so if we think about f as an operator, then the formula that we've written there is basically a way of diagonalizing this function f, expressing it in terms of a sum over these projectors.
Is that minus p in the very last bracket?
Yeah, thanks. Okay, so actually we don't have to do any more writing. The same thing is true over here. We can think about this 4-point function as an operator, which is now an operator that's taking functions of coordinates 3 and 4 to coordinates 1 and 2. So it's acting in the space of functions of 2 coordinates, pairs of coordinates. And then these guys here are again, projection operators. So if we think about it in that way, then what we're doing is we are diagonalizing this operator. We're expressing it in terms of a sum of orthogonal projection operators. And from that perspective, this coefficient here isn't the expansion coefficient in the basis of functions, it's the eigenvalue of the 4-point function. So we think about the 4-point function as an operator, then these guys are its eigenvalues. Okay, so an example of this would be in the SYK model, where the kernel of the SYK model is thought of as an operator. And we multiply it together many times to make these ladder diagrams. But that kernel is interpretable as a 4-point function in a simple field theory, mean field theory, or generalized free field theory, where we just have a product of 2-point functions. Okay. So now what we would like to do is write a formula for the eigenvalue of the 4-point function. And to make the formulas look as simple as possible, I'm going to work actually in 2 dimensions for the remainder of this part of the talk. So we can just write the eigenvalue equation. So we'll use z as a complex coordinate for the 2-dimensional space. So to write a formula for the eigenvalue, what we do is we act with the 4-point function on the simplest function that we have in the space, corresponding to given parameters delta and j. So a good example would be this one. This guy is in the subspace corresponding to the eigenvalues of the Casimirs that correspond to delta and j. And actually, this is the equation, sorry, this is supposed to be equal to something that's I delta j C1, 2. Okay, so this is just the eigenvector equation for this function, and this is its eigenvalue. So we can make this slightly simpler by putting point 1 at location 1, at point 2 at location 0. Then this factor becomes 1, and we restrict the locations of points 1 and 2 in here, and then we have this equation. So this is actually how we compute the eigenvalues of the kernel in the SYK model or its higher dimensional generalizations. It's by doing an integral exactly of this type. Now, one point is that in this expression only makes sense in the case where j is an integer, because that's required for this eigenfunction here to be single-valued at j 3, 4 equals 0. So if j is not an integer, then that expression doesn't make sense, and it's not obvious from this expression that I of delta and j has any kind of reasonable continuation to non-integer j. Okay, so this is a sort of naive formula for the eigenvalue. We can get a better formula by Wick rotating this integral, by doing the integral over points 3 and 4, not in Euclidean signature, but in Lorentzian signature. So to do that, we take z goes to u, which is x minus t, and z bar goes to v, which is x plus t. So u and v are light cone coordinates in Lorentzian space, and continuing tau to it, we find that z maps to u and z bar maps to v. So now we can write the same expression, I of delta and j. This part, I'm willing to believe, is too small to see, but, well. You can guess what I'm writing and probably see enough of it to confirm your guess. Okay, so this is the expression that we get in Lorentzian signature for the eigenvalue, but we've just Wick rotated the integrals. Now, so far we haven't done anything helpful, but it's possible now to simplify this integral by doing a contour rotation in the space of these u and v coordinates. To explain the contour rotation, it's helpful to draw a space-time diagram So here we have point 2. This is at the origin. Here we have point 1. That's at location 1 in the spatial direction. And I'm going to draw the light cones associated to these operators. And we're integrating points 3 and 4 everywhere in this two-dimensional Lorentzian space. It's, it's convenient to think about doing the integral in the following order, where first we fix the u-coordinate and integrate over all of v, and then later we'll do the integral over u. So an example of a type of configuration that we would consider, so v goes this way, u goes that way, would be one where we put point 3, let's say here, and then we integrate it over all of space, over every value of v for a given value of u. Now, the manipulation of this integral requires us to think about the complex space for v, and the two-dimensional board makes that hard. So what we'll have to do is imagine that the imaginary part of v is coming out of the board, okay? So here we have u and the real part of v, and the imaginary part of v is coming out of the board. Now, the I epsilon prescription that we get from Wick rotation says the following thing. It basically says that points that are farther this direction in u are slightly into the board, okay? So that's what the Wick rotation from Euclidean space gives us. So here we're integrating this operator over all values of v at a location which is in positive u, which is slightly out of the board. And in that case, there's nothing that prevents us from just taking this whole contour and moving it out of the board times for large imaginary values of v. We can deform the contour that way and get 0. So the integral over here gives us 0. How can we get something non-zero? So we can get something non-zero if the value of u is intermediate between the operators 1 and 2. Then it will be sort of above. Yeah, I should mention that at the locations of the light cones here, and this point is really essential, I should have mentioned it before, there are branch cuts. There are singularities that are branch cuts in the 4-point function. So I should draw them as squiggly lines. And now we're integrating this point over a contour which, because here the value of u is larger, is out of the board in front of us relative to this branch cut, but then it goes underneath this one. So now, although we can't deform this contour all the way out towards us because it's sort of stuck underneath this branch cut here, we can simplify it by taking this part of the contour and deforming it out and folding it over. So we can deform the contour to one that looks like this, taking a discontinuity across the singularity associated with this operator. And for the other operator, so let's say here we were discussing the manipulations for the integral over the point 3. We can do a similar thing for the point 4 and end up integrating it over the singularity corresponding to the other operator there. Okay. So the conclusion of this is a different formula and a better formula than this one, where we have an integral of the same type. Integrate it over region R that I'll define in a second with the same measure. But now instead of the 4-point function, we have this double discontinuity, one discontinuity for one branch cut and the other discontinuity for the other one. The discontinuities across the branch cuts are commutators inside the 4-point function. So what we get is a double commutator of operators, O1, O3, and another commutator, O2, O4. And then times the same eigenvector here. So this is more or less the final expression. And I'm going to make 3 comments about it. So the first comment is that if we like, we can reduce this integral to an integral over cross ratios. And that gives exactly Karen Huo's formula. So this is derivation of his formula. But especially if you don't know what his formula is, maybe a more important point is that this expression has an obvious continuation in spin, j. That has to do with the region over which we're going to be integrating points 3 and 4. The region that we have to integrate them over is a region like this. So here's the light cones of point 2 and 1. We're going to be integrating over a region like this, where point 3 is somewhere up here, and point 4 is somewhere down there. In this type of configuration, we have the U3, 4, the difference U3 minus U4 is between 0 and 1, and V3, 4 is between 1 and infinity. So that means that if we take the real part of j to be large here, then this integral is very happy. And in fact, you can show the integral converges if the real part of j is bigger than 1. So this establishes a good analytic continuation for this function I of delta and j. Okay, the third comment I wanted to make about it is that this expression here is exactly the retarded kernel in the SYK model. So in this case, to be concrete, this would be in a two-dimensional analog of the SYK model. And here we find that the eigenvalue of the retarded kernel, which is this operator, is exactly equal to the eigenvalue of the ordinary kernel. So here maybe I should comment on the difference from this discussion and what happens in one dimension. But let me not do that. Let me instead say why having this analyticity is useful for discussing the Regge region of the correlation function. So this is something that was worked out by Costa, Cornalba, Gonçalves, Penedones, and it goes under the name of conformal Regge theory. So it has to do with how you can evaluate the Regge limit of a correlation function in a conformal field theory, starting with an expression like this type of expression here. The idea is that in the Regge limit, contributions with large spin contribute something which is growing very rapidly. So the ordinary expansion in terms of operators, like the OPE expansion, is an expansion in terms of operators with arbitrarily large spin. And that's not a good strategy in the Regge limit, where terms with large spin are growing more rapidly, and you won't have a convergent sum. The idea of conformal Regge theory is that you process the sum over j into an integral, and then you use analyticity of this integrand as a function of j to allow you to continue to a region of j where it's not growing. You guys don't look very enthralled by that discussion, so perhaps I won't go into more detail there. But since the one-dimensional SYK model has been discussed a little bit already, let me just comment on how this is different from what happens in one dimension. First of all, in one dimension, you don't have these light cone coordinates, and so some part of this derivation should break. And in fact, it does. In one dimension, the ordinary kernel and the retarded kernel, or the eigenvalues of the 4-point function and the double commutator, are different from each other in general. The spectrum of those guys is different. But by following an argument somewhat similar to this, what you can prove is that their eigenvalues for a certain class of eigenvectors are the same. And that class of eigenvectors are these eigenvectors which correspond to conformal dimension that are integers. And those are the only ones that are growing in the Regge limit. So this fact allows you to replace the eigenvalue for those with a function that has a different continuation to arbitrary h, and is in fact analytic in the right half plane. Okay.
Is there a general prescription for how to go from one function to the other?
Yeah, there's a general prescription for the eigenvalue of the retarded kernel. In general, they're not related. They're just two different analytic functions that agree at the integers.
But if someone gives you the kernel, let's say the 4-point function kernel, can you deduce what the retarded kernel is?
You mean if somebody just gives you the eigenvalues of the retarded kernel? No, I don't know of a way of doing that, except by, well, one very elaborate way would be you take that and compute from it a 4-point function, and then analytically continue the 4-point function. That's not good. But yeah, so in Vladimir's talk, he wrote this expression for a 4-point function. He called it the 8-point function, but the 4-point function of these bilinears. And that has a complicated expression involving these C, H1, H2, H functions, which have a whole bunch of poles. If you try to take that expression and continue it to the Regge limit, then you'll have trouble with those poles. And I think what must be the case is that for his particular function, this product of C's, if we restrict that to integer values of H, there must be an alternate analytic function which agrees with it at those values of H, but that doesn't have poles in the right half plane, which allows you to continue to the Regge limit. But one's question is basically, is there a good way of guessing the function? And no, I don't know.
So do you know how these functions should behave at infinity? Is it due to...
Yeah, so this one is great at infinity. The normal eigenvalues of the normal kernel are like not good at infinity. They're at least like in the S by K model, they have these trigonometric functions in them, so it has very bad behavior at infinity. Okay, so I apologize for this sort of technical first part of the talk, but I'm going to move on now to a very vague discussion. So if there are questions about this material, maybe you could ask them now.
What does it mean to have Regge limit in quantum mechanics?
Yeah, so there what it means is the chaos limit. So you take the out-of-time order 4-point functions. The reason it's called the Regge limit is because it probes a correlation function in the bulk, a scattering amplitude in the Regge limit in the bulk. It's actually the same reason why it's called the Regge limit in conformal field theory in general. It's the kinematics in the bulk that's Regge kinematics for scattering. And in 1 and 2 dimensions in a conformal theory, the Regge limit equals the chaos limit for a thermal correlation function. But in higher dimensions, they're different.
So what do you mean by kinematics in bulk for the given boundary correlate?
So, for example, we have some kinematics where we have some highly boosted problem with fixed t and large S dominating the computation of the correlation function.
My question was more general. In general, what did you mean?
Oh, I meant, so I only meant in a large N theory. Then where we have a bulk theory, it's the Regge limit of the scattering amplitude. But the definition of the Regge limit is well defined for a quantum system regardless of whether it has a gravity dual. You just take these out-of-time order correlators and take time to be large.
The statement was that the Regge limit, if you do have a simple large interval of the correlator, is determined by the Regge limit of the bulk scattering.
Yes, that's why it was named that, yeah. Okay.
A naive statement of the analogy is that in each case you highly boost a subsystem relative to the subsystem.
Yeah, that's right, that's right. So that's the type of thing that gives you large S and fixed T. Okay. Oh, I thought of one other comment to make. I'm sorry, it's about the first half of the talk still. But the other comment is the following. We have a good interpretation of the poles of this function when we deform the contour to get the OPE expansion, the poles that Vladimir was discussing earlier. We have a good interpretation of those poles as being operators in the Hilbert space of the CFT, or states in the Hilbert space of the CFT. When we take the Regge limit, and let's say we expand at large n, we expand this function, then this function will have poles at complex values, in general complex values of j. And those are the poles that give you the behavior of the correlator in the Regge limit. And we don't have a sharp interpretation of those guys in terms of the Hilbert space of the CFT. And I think this is an important problem to try to understand what those things mean in some Hilbert space. Okay. Are there any other questions about this? Yeah.
When you define eigenvalues and eigenvectors, for the retargeted kernel, there is a unique eigenvector. But in general, the eigenvector depends on Z1 and Z2.
I'm not sure I understand the question.
In your calculation, Z1 and Z2 are fixed, right?
Yeah.
Sorry, I had something related to the SYK in mind, but I think it's just a convenient choice of Z1 and Z2.
Yeah.
For which the calculation is done.
Yeah, that's right. But you don't need to make that choice. Yeah.
Right. Yeah, I'm sorry.
Okay. So the second part of the talk is going to be different. So I'm going to make sort of a comment related to the description of black holes with long interiors. And it's a vague comment, and I apologize for that. Also, it's sort of based on it's also not very original. It's sort of based on some observations that people have made, including Lenny in his talk yesterday. So first of all, let's discuss some examples where black holes have long interiors. And I'm going to work in the case where we consider one copy of the CFT. So not an entangled state, just a single boundary black hole with a long interior. So a simple example of that would be something that formed from collapse, some matter. And this thing can be thought of as having a long interior if we look at the state at a late time, t. And there are different ways of quantifying that. One way is by looking at the maximum volume surface that touches this point. It's some very large surface. Or we can look at the Wheeler-DeWitt patch corresponding to that time. And basically, because we're up near the top right corner of the Penrose diagram, this is a very big region. So the late time, this geometry at late times can be understood as a black hole with a very big interior. So this would be in the CFT a state where we took some big operator acting on the vacuum to create the black hole, and then we evolved in time for a long time. This one is sort of trivial to make the interior small. What you do is you just don't take time that large, or you just evolve backwards in time a little bit. There are other examples. There's a whole bunch of examples, but another example, we could take this thing, and then we could act with an operator at some time in the future. That will give us a state that now doesn't form from collapse, where we have the original matter here, we have the boundary, and then we have a shock wave associated to the operator at that late time. We can then, if we like, evolve forwards and backwards or whatever and act with more operators. And what we do is we get a longer and longer wormhole. So eventually we'll get something that might look like this, where we have a crisscrossing pattern of shock waves in the interior. And a very long pattern of that type would result from applying operators. So we start out with a vacuum. We act with this big operator. And then we act with some amount of time evolution. And then some other operator. And then some other amount of time evolution in this way. And the particular geometry that I wrote here would be one where the time evolutions are alternating in sign. So we're sort of going forwards in time, acting with an operator, going backwards, operator, and so on. But there's a very wide variety of geometries that we can construct in this way and that we understand the states corresponding to them. There are all these long wormholes where maybe I should have clarified that this thing here is r equals 0, right? This is not a second boundary. and this is the boundary here. Okay, so one comment about these types of geometries is that almost anything that we do to the quantum state will make the wormhole longer. So you can sort of see that happening here, where we evolve in time and act with operators and so on, and the wormhole just continues to grow. There's really only one thing, at least only one thing that I can think of that makes the wormhole shorter, which is to undo whatever the thing was that we did most recently. So in this example here, where the wormhole got long because we just acted with a lot of time evolution, then to make the wormhole shorter, we can evolve backwards in time and come down to some earlier time, and that's just undoing the most recent operation that was applied to the state. In this case, to make the wormhole shorter, evolving forwards and backwards in time won't help. We have to, in addition, remove whatever shock waves we added to the system. So we evolve to the time where that shock wave was inserted, and then we act with W inverse. And then we go forwards and backwards, sort of cleaning up the operators that were applied to the state. That's the only way that I can think of making these wormholes shorter. Okay, so now let me discuss the...
Except for waiting a double recurrence time.
Yeah, that one actually... Okay, sometimes I wonder whether that one actually makes the state shorter, or if it just makes the state shorter in some version of the bulk theory. Sorry, whether it makes the wormhole shorter, or if it just makes it shorter in some version of the bulk theory. Okay. So now the thing that I want to discuss is a situation in which we imagine that we have a long wormhole of this kind, and I shouldn't have done that. Where we have a long wormhole of this kind, and then there's some spin deep in the bulk of the wormhole, and that spin could be in state 0 or 1, or some degree of freedom which is very far inside the wormhole. We can put the spin there just as we were making this state. We act with an operator that injects a spin, and then we continue with the recipe. Now the thing that I want to discuss is the fact that the state of this spin seems to be extremely robust to perturbations that we can make on the boundary of the theory. So there's very little that we can do by acting on the CFT that will affect the state of the spin. One way to motivate that is just to note that the whole boundary is space-like separated from this spin. And to get it closer, we would have to do a very complicated thing undoing all the operations before we could send in something that would affect the spin. And the idea is that we would like to explain or understand what property of the CFT it is that makes that thing so robust. So your first guess, and my first guess was that it should be some kind of quantum error correction property, that this spin is in some kind of quantum error corrected code, and the perturbations that we're making on the boundary are not affecting it for that reason. But I'm not an expert in quantum error correction, but I sort of convinced myself, we'll see if this stands up to your scrutiny, but I sort of convinced myself that that wasn't enough, that quantum error correction wasn't strong enough to protect against the set of possible errors that we could make. So the worst kind of error is one that was discussed by Ahmed earlier. It was in this paper of Korkulu and Maldacena, where they imagined that they were thinking about the two-sided black hole, and they acted with, let's say, a projection operator onto a simple state on one of the sides. And their bulk description of that was that it created some end-of-the-world brane in the geometry, but it left the interior basically unaffected. So we can do the same thing for these guys. And let's say we act with a projection operator on the boundary, and perhaps that gives us a bulk geometry that looks like this. So it will change and perhaps remove the region outside that brane, but the interior of the wormhole looks like it should be unaffected by this operator, where we did a projection or a measurement of the boundary state. But after doing this projection, there's no way that the boundary state contains the information about the spin anymore, because we've projected it to a unique state. And that state can't possibly know the difference between whether this spin was up or down to begin with. Yeah, that's right.
What are you assuming about that? Do you think these things have multiple states or just one?
I'm not sure state in what Hilbert space, I guess, but the spin has multiple states. I'm not making any definite statement about the relationship of this closed universe thing to the CFT Hilbert space. That's actually part of the point. But it seems like we can have multiple of these things, where we put the spin in state 0 or 1 before we acted with this projector.
Does acting with the projector mean making it, doing a measurement?
Yeah. Mm-hmm.
Something records that measurement?
I'll get to that in a second. Yeah. Mm-hmm. Okay, so now let me discuss this thing from the perspective of tensor networks. So we can have long tensor networks. A long tensor network just corresponding to time evolution might look like this, where this is some, I'm not going to shade in all the tensors here, but this is some tensor network that corresponds to the quantum circuit representation of the time evolution operator. And as time gets longer, then this thing gets longer and longer because we have to add more layers of this quantum circuit to prepare the state. So that's sort of the tensor network analog of the first picture, of these pictures with many of these operators inserted with time evolution going in different directions. We might have a tensor network where we have time going this way, and then some operator, something like this. Some quantum circuit where we're evolving forwards in time, acting with operators backwards, and so on. But as we add more of these operators, the tensor network gets longer in parallel to the bulk geometry, and actually there's a sort of detailed correspondence between the geometries of the wormhole and the geometry of the naive tensor network that we would use to describe the state. So from this perspective, it's also sort of clear that this spin maybe here is like related to some extra tensor that we add in the tensor network. And it's sort of clear that this thing will not be affected by just acting with more time evolution or acting with operators here. So the tensor network picture seems to incorporate the right type of robustness against boundary perturbations. So let's examine now in tensor network language the measurement or projection that we made. Yeah?
Somehow it should be important that this is the radial direction and that's time in the two
Oh,
things are not.
sorry. Yeah. This is all, there's no time here. This is just, this is like maybe sort of like a spatial slice through the bulk. I didn't mean that these pictures should correspond to that picture. In particular, this direction here, these are just the different tensors representing different subfactors of the boundary Hilbert space. It's just some different tensor that we added here. So in order to create the spin in the bulk, the way you do it is as you're building this wormhole, at some point you act with a different Hamiltonian that shoots a spin into the system with state 0. So I haven't done the projection yet, so you're not allowed to make comments about that. Raghu, did I answer your question or not?
Sorry, my question was just that, is the horizontal direction in both the diagrams the same or different?
Yeah, it's roughly the same. Yes, but that's sort of a non-trivial statement. But yes, there's a detailed geometrical correspondence between this picture and a spatial slice through that picture.
So the right arrow and the left arrow correspond to evolving forward and back.
Yeah, that's shorthand for which types of tensors are in that part of the network, whether they represent forwards time evolution or backwards time evolution. Okay, so now we do the measurement in tensor network language, and that looks like something where we start with this, and I'll do the measurement in a way that will make Lenny happy. Actually, I think this drawing is from one of his papers, where we do something like this. Here's the apparatus that records the outcome of the measurement, and here's our system. So there's some kind of a junction in the tensor network where this would be a tensor network representation of the state where we made a complete measurement of the system at this time. And again, this seems to sort of respect the picture that the stuff deep inside the bulk or at early times in the tensor network are not affected by what happens here. So we'll still use the same type of tensor network to describe this part, as we would have done if we hadn't inserted this measurement. Okay, let me try to do better. So the tensor network is some kind of lattice on this space where the lines correspond to indices and the intersections are the tensors. So what this drawing means is that at this point we have a sort of a y tensor. So a y tensor like this. And that represents a measurement where the outcome of the measurement is recorded by this system, and then we proceed on with our evolution. Is that?
But we proceed with tensor networks on both branches?
Well, that depends on whether the apparatus that measured it is experiencing time evolution of its own. In drawing this thing as extended, I'm assuming that it is. Like it's living somewhere and it has a Hamiltonian that's acting on it and generating a longer and longer circuit. That's not at all important, yeah. Actually, the whole point is that none of this is important. This part doesn't care. The only thing that would change this, again, from the perspective of tensor networks, would be if we undid everything that we'd done so far. We reverse the quantum circuit and go back. So I said that comment slightly out of order. The thing I wanted to say first was that you could object that this tensor network is just some tensor network description of the state. And maybe it's not the one that we're supposed to identify with the bulk geometry. And although I don't have a great answer to that, my belief is that tensor network representations of low complexity states are like almost unique, in the sense that the number of parameters in a quantum state is exponential in the entropy, and the number of tensor networks that you can write down of some length is like proportional to power of the entropy times the length. So if you're lucky enough to have a tensor network representation of a state, then you're not likely to have another one which is sort of non-trivially different. So that states, low complexity states, almost define a unique tensor network, up to stupid things you can do where you cancel some set of tensors locally against another set of tensors. So the idea is that in this setting where we had some evolution, a measurement, and then some further evolution, there won't be another tensor network description of this state that isn't extremely large. This is in the spirit, I think, of Lenny and Scott Aronson's conjecture about the growth of complexity.
Why not just say the smallest tensor network that you can draw?
Well, because I don't like that language. I agree with the sentiment. The language sort of suggested to me that there might be a lot of tensor networks of all kinds of different lengths. I think the reality is that,
You go back and forth and cancel out things.
well, I think the reality is that up to those trivial cancellations, there's probably a short tensor network, and then there's nothing until you get to extremely long lengths. So it isn't so much, for me, the shortest tensor network as like almost the unique tensor network that's useful. But that's sort of a minor point. Okay, so this was some discussion of, and now one very vague interpretation of both of these things. Yeah, okay, so we would like to then ask the question, what is this in the CFT? Like, what is this spin in the CFT that's so robust to these types of perturbations? And I think a sort of way of thinking about it that's been helpful for me is to think about that as being the past history of the state. The region behind the horizon of the black hole is like everything that's ever happened to the quantum system that we're examining. So that sort of agrees with the bulk picture that we were drawing there, where as we added more and more of these perturbations, they were recorded with these shock waves or by the shape of the wormhole inside. And of course, it's consistent with this picture of the tensor network, where literally the tensor network that you write is just basically following the quantum circuit that you use to prepare the state. So in tensor networks, it's sort of clear that this part of the network deep inside is a history of the recipe that you followed to make the state. And that recipe is more or less unique, so it's well defined to talk about the history of a quantum state. And the idea is that that's what the interior is representing. So,
Is it fair to say that this is what Ying Zhao called the tape? Tape description of the...
yes. Yeah, the tape, I don't remember. I might be missing a subtle point regarding the existence of two tapes, but yeah. Mm-hmm.
Are you going to talk about the projector on the right?
The projector? The idea is that here we've seen why the projector doesn't affect this. It's implemented in tensor networks in this way. That was the comment I want to make about the projector.
This picture is not a single projector. This is the sum of all...
Yeah, that's the measurement process. But it's important that after the measurement, the information isn't in the system at all. So you can't quantum error correct your way back to getting that spin. It's no longer in the system that was measured. It's in the combined system of the system and the apparatus that measured it.
If you view it as history, you could also draw the picture in the middle blackboard and say, well, that was the history, and
Which one?
the one in the middle blackboard.
This one.
No, the one on the right.
Yeah.
That was the history that ended up with the measurement.
Yeah, I think this is the part that's common to everything, is this part. And then there will be a somewhat, yeah. I mean, the complete history of the system that was measured will include this, and then it will include this. I think if we insist on describing it in a unitary way, it will include both pieces. Maybe I didn't understand the comment. Okay.
Just that it's not relevant to saying what the spin is, what happens in the future.
Yeah.
Whether you have the Y junction or not, or you decide it as a closed universe.
Doesn't affect the spin. Yeah.
So closed universes are sort of histories that start and end.
That start with something and end with a projection. Yeah. And there's and I think, but they're probably only well defined if they're part of this larger system where, yeah. Okay. Yeah. One point that this history thing, oh, sorry, yeah.
So there's this thing I'm not understanding. So if I have a state of the spin in the past, what is it? I don't understand what you mean by saying making a measurement in the future does not affect the state of the spin. Because if I make a measurement, it'll collapse whatever the state of the spin was, unless it was somehow very non-locally encoded and I made a very kind of soft measurement. I just don't understand.
Yeah, that's because part of my claim is that the description of the spin is not an operator in the Hilbert space. It's like the history of the state. It's what happened to the state in its childhood. And you can't change that by acting now. You just can change the present and the future by acting now. So that's something which is true of like the past in the world, right? But it isn't a property that follows really from some error correction. So, okay, so the question, what was the state of the system 5 minutes ago, is not a question that we can answer without knowing what the evolution was between 5 minutes ago and now in an operator form. So we can't do it in an operator form without knowing the evolution between then and now. But for low complexity states, it is actually a function of the state. And we don't need to know what happened between 5 minutes ago and now because we can figure it out from the state now. So if somebody tells you, here's a low complexity state, if we analyze the wave function of that state, we will learn everything that happened to it. So that allows us to strip off the last 5 minutes and then ask the question about the spin.
Not literally the way you're saying it, because we don't learn anything about the time dependence. We only learn the sequence of steps by which it evolved.
We learn the time dependence too. Time dependence has to be implemented by a representation of the time evolution operator.
Well, but you said you wanted to assume you didn't know the Hamiltonian.
Yeah.
Multiplied by 2, and then it took 10 minutes. 2.5 minutes.
Oh, sure. Yeah. But that has to do with.
So you really only learned the sequence of quantum states that you evolved from.
You're right. What I guess yeah, that's right. Sorry?
Did you just deduce the existence of diffeomorphism invariance somehow?
Yeah, yeah. Well, you can only tell sort of what happened to the state, and it doesn't care whether that was twice the Hamiltonian for half the time. Yeah. Yeah. Yeah.
This picture of a spin in space-time doesn't seem right. If you say there is some quantum information in the bulk, it cannot be localized both in space and time. And
Yeah, sorry, I didn't mean that it was only at that location. I mean, the spin follows some trajectory, right? And we'll follow a trajectory like this.
yeah, but how do you insert the spin into the system?
I insert it, so let's go back in time. We remove a bunch of these shock waves, and eventually we reach a time where the boundary was here. Now to insert the spin, I act with an operator at this time. And then I will act with this shock. After acting with that shock, I have this state. Sorry, I should draw it better. Should I draw it better?
Yeah, it helps.
So let's go back to the early history here, where this perturbation is there. And let's say we also acted with one. Okay, so we have this geometry. So this is the geometry where we have this shell, the infalling matter, and then we acted with one perturbation at this time. To inject the spin, we act at this time with something which inserts a spin here. And the spin will follow some trajectory like this. Okay? Okay, so now the spin is in some location here. And if we like, we can act with further operators, which will make the wormhole longer. So we could, after that, we could act with an operator at a later time, and we'll find a geometry where we have this perturbation, we have the spin somewhere here, and then we'll have other shock waves.
I'm not sure.
If you like, the spin could be just the state of one of these shock waves. So the shock wave carries some energy, and it also carries some internal degree of freedom. So here we have a picture with many shock waves, and if you like, the spin is just an internal degree of freedom that's attached to one of these shock waves.
I had exactly this picture in mind. It's not that the spin is protected from errors, because if we inject the spin by sending a shock wave, and then like in the Haydn-Pascal protocol, later we take out some piece of this system.
Mm-hmm.
This piece will contain the information about the spin relative to the thermometric double.
Yeah.
And once we take it out, there is no way to recover the spin. But taking this piece out is like sending another shock wave back in time. And after the second shock wave, the spin can only be recovered if we know what we have taken out. If we don't know, then if this piece is missing, there is no way to recover it.
Yeah, that's related to the fact that this spin isn't an operator on the Hilbert space of the black hole. It moves to whatever system I mean, I believe that's similar to this discussion with the projection. We need to do a pretty complicated thing in the case of a one-sided black hole, like a complete measurement. But in the two-sided black hole, we can do a measurement of a small part of the system, and then the quantum information moves to that thing plus whatever we were entangled with.
Yeah.
But I think from the bulk perspective, we would say that if we do that operation, the state of the spin in the bulk has not been changed. The description of where the quantum information is located in the dual description is different. It's no longer in the CFT, it's in the thing that was entangled with it plus the small piece that you measured. But so that our description of that will be in a different place, but the bulk picture seems to be the same.